let's continue to study how we can apply the geometric series in business math. Let's use this example to study it in detail. So we have an investor that saves 1,000 euros at the beginning of each year to a savings account, earning 2% annually. And the savings are made annually during the years 2006 to 2014. And then we're interested in knowing the balance in the beginning of year 2014. The main difference compared to the arithmetic is now that you notice that the deposits are made annually and they're accruing interest for several whole years. So what it means that we need to now apply compound interest in order to calculate these values. And please notice another thing, that in compound interest we're always going to the maturity value. So we can go directly to the balance, so we don't have to calculate the deposits and the interest separately. Alright, let's start working. And we will do the same kind of a trick, that we still think that each and every deposit is made to a different account. And we calculate how much each of them will grow until the beginning of 2014. That was the time we were asked to calculate the balance. But we need to do another trick. We will start from the last deposit. Okay, let's have a look. So, the last deposit was made in the beginning of year 2014. So, 1,000 euros. And then we were asked to calculate the balance in the beginning of the year 2014. So it means that this last deposit does not have time to grow any interest. Alright, let's think about what was happening a year earlier. So we're going backwards. So now we are thinking about year 2013. So the deposit made in year 2013 was also 1,000 euros, but now, since it was done a year earlier, it has grown interest for 1 year. So the deposit multiplied with 1 plus rate to the power of how many years? So now simply 1. So that one deposit by the end has grown to 1,020 euros. Let's keep on going backwards. So now we go to year 2012. Once again, deposit 1,000 euros. We think separately on a separate account, but that has grown interest for 2 years. So from 12 to 13 and 14. So now the exponent is 2. So what is happening here is that every time, once we reverse 1 year, the exponent grows by 1 unit. And actually what we are doing every single time, we are multiplying with the value 1.02, going from the first to the second. And then we multiply again by 1.02, and again 1.02, which is indicated in the exponent. So what we can see here, that now the maturity values, those create us a geometric series. And once again, series, we're not interested in one individual deposit, we're interested in the total amount we have at the end of the whole interest time. So, how did we then calculate the sum of geometric series? The formula was like this. So we needed to know the first value. And now you probably noticed why we did the trick that we started from the last one. Because the last one is simply the amount of the deposit. So it's an easy value to choose if you start from the back towards the new values. Also, another thing, the Q was the common ratio, so the value you multiply or divide to go to the next value. So now it is the 1.02 in our case. So 1 plus rate. So that's another reason why it is reasonable to start the series from the latest deposit towards the older ones. Okay, let's put in the values here. So the calculation would look like this. So there are a total of 9 deposits. Please notice that the n is now how many deposits. So 9 totally. And also, if there would be no interest, you would have simply 9,000 euros. So now you can see the effect of compound interest. So gaining interest on interest. So we have quite a bit more than just 9,000 saved on the account. Once again, we usually write this using business math notation. And then we actually don't talk about sum of geometric series. We talk about FV, which is short from future value. So it looks familiar. We have calculated future value formula in Excel earlier when we were calculating compound interest. We are still applying the same formula. But now what is different is that we have a payment that is repeated every year. Earlier we had only PV, one value in the beginning, but P and T refers to the value that is deposited every year. And then 1.02 was 1 plus rate to the power of n how many deposits, and then minus 1 was coming from the formula. And here in the divider you can erase the ones because you have plus 1 and minus 1, so you have only rate remaining at the end. So let's summarize this calculation. So we would be applying this last step, the future value formula for a case like this, and the calculation looks like this. And one important thing I want to focus and point out. The last deposit was made at the beginning of 2014. So the balance we are just calculating here is also at the beginning of 2014. So it's kind of a built-in assumption in the formula that the future value is at the same time as you make your last deposit. We will talk about more of this issue in the next topic, which is periodic payments.